continuing where I left off last time with these limit properties. Suppose you know that the limit as x goes to a of f of x and the limit as x goes to a of g of x exist and are finite. It means infinity is not one of the answers to those things. Then the limit as x goes to a of f of x plus g of x is equal to the limit as x goes to a of f of x plus the limit as x goes to a g of x. Let's just do a quick example. I think I've had this. I'll use the same numbers I did, the same functions I did before. F of x can be x squared plus 1. G of x can be 2x minus 3. And I'll look at the limit as x goes to negative 1 again. Yeah, there we go. What I'm going to do last time, I've already changed the last function to be the sum of the other two functions. So let's copy that and paste. The pinkish looking one is the sum of the two functions. F of x is the parabola, g of x is the straight line, and f of x plus g of x is the pink parabola. For some reason I want to say fuchsia, but whatever. Now look at as x goes to negative 1 for f of x. We already done this, but this just to remind you, just look on the graph. There's no holes or breaks or anything like that. So I can just read off the y value. At the point negative 1, 2, the y value is 2. So the limit as x goes to negative 1 of f of x is 2. G of x, the point negative 1, x negative 1 corresponds to y negative 5. So the limit as x goes to negative 1, g of x is negative 5. The limit as x goes to negative 1 of the sum of f of x plus g of x equals. Now we're going to look at the composite one, which is the pink parabola. Look at the point for x equals negative 1. The y value is negative 3. So the limit as x goes to negative 1, f of x plus g of x is negative 3. And this is verifying what I just wrote, because 2 plus negative 5 equals negative 3. So move on. Let's talk about some more basically, this is a very dry section. A lot of properties and some verifications of those properties. Later on, we'll get into more heavy stuff. If the limit as x goes to a of x to the n equals a to the n, where n is a positive integer. Well, the reasoning behind this is we can apply the product rule, let's call it that. I can say the limit as x goes to a of x squared is the limit of x goes to a of x times x, which I can break up into the limit as x goes to a of x times the limit as x goes to a of x. Now we already know that the limit as x goes to a of x is simply a. So this results in a times a, which is a squared. Now then, I can extend this. You may remember something called inductive reasoning. Well, that's what I'm using here. If I'm looking at the limit of as x goes to a of x to the n, I can think of that as the limit as x goes to a of x to the n minus 1 times the limit as x goes to a of x. Now, conceivably, we would have shown that a to the n minus x to the n minus 1 goes to a to the n minus 1. We already know x goes to a, and so a to the n minus 1 times a gives us a to the n. This is the start of explosive growth in some of the properties that we're going to have now. So, for example, suppose p of x is a polynomial. You can pause here if you need to go and remind yourself what that is. But if it's a polynomial, if p of x is a polynomial, then the limit as x goes to a of p of x is equal to p of a. That means I can, for polynomials, I can just plug in a. I sort of have a little derivation of this. If you think of it as written as p of x equals, I think a was a bad choice. Let's call it c sub n x to the n, c sub n minus 1 x to the n minus 1 plus dot 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 plus c1x plus c sub 0. You should be familiar with this type of a function. The limit as x goes to a of p of x then is the limit as x goes to a of that expression I just said, c sub n x to the n plus dot 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 plus c1x plus c sub 0. Now I can use the sum rule to break up this into a bunch of limits involving the addition. So I can take cn x to the n and split it off from cn minus 1 x to the n minus 1 dot 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 plus the limit as x goes to a of c1x plus the limit as x goes to a of c sub 0. Now those c's are all constants. They're just real numbers. Now then I can apply the product rule for each of those cn times x to the n's and break those up into limits. The limit as x goes to a of c times the limit as x goes to a of x to the n plus dot 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 the limit as x goes to a of c1 times the limit as x goes to a of x plus the limit as x goes to a of c0, which I already knew that one. The constants are not affected by limits, so the limit as x goes to a of any of the c's are just those c's. However, x to the n turns into a to the n, x turns into a, and that is equal to p of a. So somehow the integers are able to make up numbers of all types. Well, it's the same thing here with rational, not rational, but polynomials. They're sort of like the integers of the function world. Here, if the limit of x goes to a of f of x and the limit as x goes to a of g of x exist and are finite, then the limit as x goes to a of f of x divided by g of x equals the limit as x goes to a of f of x quantity divided by the limit as x goes to a of g of x, provided that the limit as x goes to a of g of x does not equal 0. All right, I'll pause there.